So we're trying to write equations of lines. Hopefully that sounds familiar. We're acting like we never did that before. Right? We've written equations of lines as we did last time? Yes? Am I right about that?
Yeah.
Okay. A lively bunch today. Y equals mx plus b. Get the slope there. And the y-intercept. So we could fill in those two things, we'd have the equation of a line. So first problem is very simple, yes? Because it's just given to us, the slope and the y-intercept. So the equation is just fill in the blank. Negative 5x minus 1 plus negative 1. Right? So that's what we're doing, trying to, in each of these is get the slope and the y-intercept. And once we have those, then we can finish the equation of the line. We can fill in these pieces. Okay? This one's not as easy. They don't just tell us what the slope and the y-intercept are. They give us some other information. They give us a point. Right? They give us 1 point, not 2, just 1. And then they tell us this, perpendicular to y equals 4x plus 1. Does that tell us where another point is found? Does that, I mean, directly, does that directly tell us where the other point is, where another point is? Yes or no? Does it? No, it doesn't. What does this information tell us about? The intercepts? It tells us the intercept of the line that goes to this point? Or is it like the slope? Yeah. To say something's perpendicular to something else is to compare their slopes. That's exactly what we're comparing, is the two slopes. Right? The slopes of two perpendicular lines are what? I'm imagining that we've done this before. Yeah?
Well, you take the slope and
Yeah.
flip it over
Right,
to
reciprocal.
1/4 and negate it.
Right, and negate it. So we negate it and we flip it over so it's the opposite reciprocal. So the slope for this line is what?
Negative 1.
Well, okay, for this one though.
Oh,
Is 4, and so if we take the opposite reciprocal for this red guy here, the slope will be what? Negative 1/4. We negate the reciprocal. Okay. So we have a slope and we have a point. Well, that's not quite as easy as this, right? It's not a, the point they give us is not the y-intercept. We do have the slope now. How do we proceed? How do we get the rest of the information to write the equation of the line?
Once you plug negative 1 to the y and 3 to the x.
Okay, so we've got this equation that we want to complete. Yeah, and we've got part of it. We really want this guy right here. But what we do have, we don't have b, but what we do have is that Daniel said an x and a y. So a negative 1 for y, negative 1/4 times x is going to be 3 plus b. So negative 1 equals negative 3/4 plus b. So to solve for b, we add 3/4 to both sides. Negative 1/4, so b is also negative 1/4, and the equation of our line is y equals negative 1/4 x minus 1/4. Last class was more energetic. What's up with you guys?
It's just Friday. I just
It's
Friday.
Friday.
Almost just got done March.
Friday, March day.
I
Okay.
have no idea what to do.
Didn't we do this in the last class though?
I was gone.
Didn't you watch the lecture?
Nope.
Why did you two?
Nope.
Did I put there for free every day?
Yep, I forgot.
Oh, okay. Want to do that? Huh?
I need to.
Oh, yeah, okay. We'll skedaddle. Okay. See you later. Enjoy whatever it is you're leaving this class to do. Yes. All right, again, writing equations of lines here. We have a point, that was useful back here. We have another point, so they didn't tell us, they didn't tell us the slope this time. So what information are we supposed to glean from these 2 points?
The slope.
We can get the slope with 2 points? Of course we can, that's like almost the definition of the slope, right? The slope will be what?
8 minus -2 over.
Right,
negative
y2 minus y1, x2, oh, that's supposed to be a 2, x2 minus x1. So 8 minus -2, that's 10, -3 minus a -5, gives us 2, slope of 5. All right, we got the slope, we got 2 points. Now what? Daniel, do all the work. What's that?
Pick a point.
Pick a point, and then what?
Basically what you did for 25.
Same thing as we did here. We plugged in a point, x and y. We'll pick an x and y here and plug them in. I'm going to pick the one that has at least one positive value. I like positive values. So 8 equals the slope 5 times x, -3, plus b. B equals, let's see, we got 15 here, -15 here. Add 15 to both sides, you get 23. So y equals 5x plus 23. Okay, that was 2.4. That's all the 2.4 stuff, writing equations of lines. They can give us a point and a point and a slope, 2 points, a slope and a y-intercept. That'd be the easiest case. They can just tell us the point and another point, which means we can find the slope, and now we have a point and a slope. Give us a point and information about the slope, like if it's perpendicular or parallel to another line that has a slope that we know. Okay. Are there any questions from that? Okay. Shall we move on to the next 2 questions? Yes? Okay. Talking about direct variation here in 2.5. So if y and x vary directly, that has a really specific meaning. And what is that meaning? What does it mean that y and x vary directly? Well, there's lots of functions. They're not all direct variation. We wrote it down a couple times, a few times. Said that y varying directly with x means something specific. Yeah.
I know there can't be a y-intercept for it to be a direct variation.
Okay. Now, not that there's not a y-intercept, but the y-intercept is 0. Okay. So, all right, we have the equation of a line where we just have plus 0. There's no b, so we'll just back it up. No b, just y equals a times x. So if you take x and you multiply it by some number, and that's all you do, and that gives you y, we're looking at direct variation. And this guy's called your constant of variation. Okay. So the question is, does this look like this? Does that look like that? Does it look like y equals a number times x?
Not yet.
Not yet, so it could. How can we make it look that way? Yeah.
Add 5x to the other side.
So we're going
On
to
both
solve
sides.
y. So 2y equals 5x. Divide by 2. Y equals 5 halves x. Does it look like that now? What's that?
Yeah.
Yeah. It's okay if a is not a whole number. It can be a fraction or decimal or whatever. As long as it's just a number times x equals y. That's all that matters. Okay. Well, does this look like that? Then we take x, multiply it by a, and that gives us y here. Can we multiply x by a and get y? What do we multiply this by to get y? Reciprocal of 3. Just that? Just the reciprocal? 1 over 3. Oh, but it came out negative. The negative 1 over 3. All right, We multiply by negative 1 over 3. Does it work here? Negative 1 over 3? Multiply by negative 1 over 3? Yes? Yes? It keeps working. What's the equation then? Y equals negative 1 over 3 times the variable x. That worked real nice. Are there any questions from the quiz or from some other part of the homework? Yeah.
Question 17.
Of which section?
25. From 2.5.
2.517. 2.517.
I think that's. I have to get that first. I think so. No.
The multiple choice question?
Uh,
Oh, it's not that one.
Sorry.
Did you have a question? You just don't know which one it was?
Yeah.
Do you think you could find it if you took a second?
Could you do 17 and do that then?
Huh?
I guess you could do 17.
This one right here?
Yeah.
Multiple choice question? Which equation is a direct variation equation? Is it A, y equals 2x squared? Is it direct variation? No,
yeah,
because,
this is which equation is a direct variation equation.
right? So is A a direct variation equation? No, why not? It's a number times x, right?
There's an x.
It's squared, right? That's not what we specified. It's just y equals a number times x to the first power. B, so it's not A. B is y equals 1/6 times x. Is that direct variation? It is. So we're done. We're so confident we won't even look at the other ones. Which is a direct variation equation? Oh, that has a solution of 3, 18. Does this have a solution of 3, 18? Yes, that's what we're supposed to ask.
So that's what
Oh, okay. So 3, 18, what does that mean?
it's a point.
It's a point, right? And what is this? That's x, and this is y. So if I plug this in for x and this in for y, then, well, it should probably be equal, right? Because it says they're equal. So is this a solution to this equation? Put a 3 there, and an 18 there. Is that right? We get 3 over 6, right? 1/6 times 3 is 3/6, that's 1/2. Okay, so it's not that one. It is direct variation, though. C, y equals 6x. How about that one? Does that have 3/18 as 3, 18 as a solution? Put 3 in there. 3 times 6 is 18. Now look at that. That's exactly what we're supposed to get. Yeah. So if you're looking at a function like this, the solution is any x comma y, then when you plug in x and you plug in y, this is true, right? This might be equals, this might be greater than, this might be less than. Whatever it is, whatever the sentence says, it's true when you plug in a solution. And it's false when what you plug in is not a solution. Okay? Let's, there's more questions? Any more questions?
Let's get 38 on 2.5.
38, 2.5. 2.5, and Nathan might have one. The time it takes a diver to ascend safely to the surface varies directly with the depth. Okay, so we got variables t and d. The time it takes varies directly with the depth, right? or t varies directly with d, right? It's the same as y varies directly with x. If we're saying that, we're making a statement about the equation that relates t and d, right? If t varies directly with d, then what kind of equation can we write for t and d? T equals d? Oh, okay. Well, this is like y and this is like x, right? We could, that certainly is true, d would equal at. But just the order they wrote it in, when they say t varies directly with d, then we, like, if you write it from left to right, you'll kind of write it in the same order that they said it. T varies directly with d. Now, we could rearrange this so d equals the number times t, right? That number that you'd multiply by t would just be the reciprocal of a. Multiply by the reciprocal of a equals 1 over a times t. That's just a number 2. So that works just fine. But just the order they said it in, this is how you can assume they meant for you to write it down. It takes 0.75 minutes for safe ascent from the depth of 45 feet. Write an equation that relates d and t, then predict the minimum time for a safe ascent from a depth of 100 feet. So they give us a solution to the equation. It takes 0.75 minutes to rise 45 feet. 0.75 minutes to rise 45 feet. So what does this information allow us to do? To do what? Find the slope, yeah, find the slope of the line. Find A. So A equals 3/4 divided by 45. That's 15. So 4 times 15 is 60. So 1 over 60. Just turn 0.75 into 3/4. Divide by 1, or divide by 45 is the same as multiplying by 1 over 45. 1/60th. So the equation that they're asking for, we just plug in A. Y equals 1/60th x. And then they say to make a prediction about the minimum time for safe ascent from a depth of 100 feet. How are we going to do that? I guess I shouldn't have written it the way I did, should I? Because we're working with T and D. So how long should you take at least to rise from 100 feet? Or how do you find out? Yeah.
Should do 45 over 100 is equal to 1 over 60.
Set up a proportion. You could. But we also have, I mean, it's going to be the same thing, but we have this depth of 100 feet. How long is it going to take? Well, how long it's going to take varies directly with how deep you are, so you could just plug that in. T equals 1 over 60 times 100. So 100 over 60, or say 10 over 6, 5 over 5/3 minutes, or 1 2/3 minutes. Nathan, do you have a question?
Number 30.
Same section? Yeah. Give an example of two real-life quantities that show direct variation. Okay. So, when in life, can you plug a number in for x, multiply it by a constant, and that gives you some result that makes sense? So kind of a measurement, okay?
If you're converting something,
Okay.
like
Converting from
centimeters to meters or something.
Centimeters to meters. So if we plug it in centimeters, and this is meters, then what is A? Okay, so let's test it out. So we got, let's make it easy, 100 centimeters. Plug in 100 centimeters, and we multiply by 100. Okay, but we're close, aren't we? What's that? 0.001. 0.001. I think you're 1 0 off. I think it's 0.01. Or 1 over 100, right? 1 over 100. When you divide by 100, you move the decimal over 2 times. That'd be 0.01. So we take 100 centimeters, we multiply by 0.01. We're going to move the decimal place over 1, 2 places to the left. 100, moved it over 2 times to the left, that gives us 1 meter. Yeah, that works. Good. Converting units, that could work. What about another one? They asked for 2. One more.
Feel like shipping orders kind of work.
Shipping orders in what way do you mean?
Like for how many, like, you get so much money for like how many boxes you sell or something.
Okay, so you would plug in a number of boxes.
Mm-hmm.
So number of boxes. And then what would you get out?
Like the price of all of them together.
That's them all together, so you know, some total cost.
Mm-hmm.
Right? And so what kind of number would have to go here?
How many or
It would be how many
Probably
shipments from it.
It'd be the price.
The price of each box.
Price of each box. So if we're looking at $5 a box, and we order 100 boxes, and they're $5 a box, $500 is how much it costs. Yeah, that works too. If you think about a lot of these that I can think of are conversions from one unit to another, right? Unit of boxes to a unit of dollars. We could do, there's D equals RT, right? Instead of Y, we're using D, and instead of X, we're using T, where this is the time, and this is the rate, and this is the distance. If you're traveling at 60 miles an hour for 5 hours, you multiply this together to get how far you traveled, right? Distance equals rate times time. And plenty of other examples. There's 3. Well, that'll do it. Unless there's more questions. Okay, let's pass it our homework. Remember, name and ID right there. Oh, gosh, well, I mean, we do have one.
Yeah, you're like 6:48, which is good.
Yeah, sorry.
Alright, you guys stay by the way. I'm going to the game afterwards. You going to the game afterwards?
Okay. All right, let's get started on 2.7. We're going to go through 2.7, and we're going to get through a little section at the after 2.7, 2.7 extension, but that'll be it. Okay. So here's what I want you to do. I want you to get a piece of paper, a pencil, a pen, whatever, because we're going to use it pretty extensively today. And let's talk about function. I can even. One analogy that I really like for a function is a factory, and I think maybe I have one here. smokestack and stuff. And what factories basically do is take things into them, put things out. Right? We've talked about this before. Right? What do we call the things that go in? Input. What do we call the things that come out? Outputs, yeah. So that's we're going to be working really extensively with this idea. And you can, again, I've said this before, and I'll keep saying it, if you can think of a function as this thing that turns input into output, you can take stuff in and stuff comes out. What happens inside the function, what kind of things does it output? If you can think of a function in those terms, it'll make it so much easier for us to talk about a function. And to talk about what we're trying to do today and lots of other days. So I'm going to give you a function, and I want you to think about what, well, the inputs are not that interesting. We're going to put stuff into it like 1, 2, 3, 4, -5, -6, whatever. The stuff that comes out of the function, that's what makes it a function different from another function. Right? Most functions take in the same inputs, but they put out different outputs. That's what makes them interesting. So I want you to take this function and I want you to see what kind of outputs you get from it. Then I want you to graph it. Okay? And remember, a graph is just a representation of the function, just like the equation is, just like ordered pairs, just like a mapping diagram or a table of values, whatever. So I want you to take this function, y equals, well, y equals what? What is that? The absolute value of x. So I want you to just take it, draw some axes, and graph it. Okay? Graph some inputs and some outputs, and then once you have what you think is an idea of what the overall shape would be, just connect those dots in the shape that you think it should be. Okay? Go ahead. On your notes. Draw some axes like this to start with. Okay? And maybe write y equals the absolute value of x. Function is just input and output. It's in, stuff comes out. This axis is where you'll find inputs. This axis we can call the output axis. So all the graph is showing us is this input gives this output. So can you find some of those inputs / outputs? Another little push. Anytime you have a function, an equation, let's say, and you want to graph it, you don't know what it looks like. You don't know if it looks like a line or if it looks curvy or if it looks like a circle or a square. What does it look like? how can we start to get an idea of what this function looks like, or where this function exists on the graph, on that plane? Anyway.
Put in numbers.
Put some numbers in a function. Put some inputs in and see what outputs come out. And when you find those things, then plot them on the graph. Okay, so so here's something. I'm noticing that some of you will put in, say, 4, right? Put 4 into the function. Put 4 into the absolute value function, what do we get out? 4. 4. We get 4. Okay. Seen several of these. We put in 4, right? And we got out 4. Okay, it kind of makes sense. Like I can see why you do that. But the thing about a graph with basically what we have is 2 number lines. What we have are 2 number lines, an input number line and an output number line. Okay, and by putting these two perpendicular to each other, we can graph the relationship between 2 numbers, which is that if I put in 4 and I get out 4, that translates to the graph. You put in 4. And now to say when you put in 4 what you get out, you go vertically to that value. You go vertically to 4. So put in 4, get out 4. That's what's meant by 4 comma 4. It means that I put 4 into a function and 4 came out. Okay? So there's one point. What's another point? 6 comma 6. How about some negative ones?
Negative 4, negative 4.
Negative 4, negative 4?
Positive 4.
Positive 4, I mean.
What does the absolute value mean?
How many spots away it is from 0 on a number line?
How many spots away from 0 it is. So negative 4 is 4 spots away. Okay, so let's start plotting these guys. Negative 4, 4. Yeah, we did that. And 6 comma 6. You feel like you know what that graph is supposed to look like with those 3 points? I feel like not quite.
Basic. 0 as x.
Put in 0 as x is good. Put in 0, 0, and now count how far away is 0 from 0. It's 0 places away. So 0, 0.
Always good.
0 is good. 0, 1, working your way out from 0 is usually a good strategy. 1, put in 1, you get out.
1.
Put in negative 1.
1.
So we got a 1, get out 1. In negative 1, out 1. Starting to look like something, right? Does it look very curvy? Like it would have much of a curve. It doesn't look like that to me. If you're not sure, then just plug in some more points. 2, you get out 2. 2 comma 2. Okay. No, it seems like we're just going up 1 over 1, up 1 over 1, up 1 over 1, up 1. That's not very surprising, really, because if you think about it, and you graph y equals x, not the absolute value of x, but it's x. They're almost the same function, except for this one always gives you positive or 0. It'll give you 0 if you put in 0. Okay. Well, y equals x, so that's just y equals 1x plus 0, so y-intercept is 0 and a slope of 1. So we would go right here, we'd go up 1 over 1, up 1 over 1, just like this one is doing. Just like that. But then we'd also go down here. This one isn't doing that. This is this line, a line we're used to graphing. This one's just like that line. It has like this up 1 over 1 pattern. But it, when it gets down here, goes the other way, like a mirror image of that part of that line. Because that's what the absolute value function is. It's just like an always positive output. Okay, it's very optimistic function. It's always positive. Or 0. Okay, so I'm seeing, I think maybe some rustiness when it comes to graphs. Right? So, again, we'll jump back here to this page. A function takes things in and it puts things out, right? And a graph is just like it's an efficient way to list all of those inputs and outputs, right? If you were a guy and you worked at this factory and you kind of wanted to keep track of what was going on, you might have a little clipboard here. I'm gonna draw a clipboard. I like drawing things. Okay, you got a clipboard, a little spring back there. You got a piece of paper, and you just start writing down the stuff that happens in this absolute value of X factory. You put in a 1, out comes a 1. Okay, so now you gotta keep track of that input and output. You can do it lots of different ways. You might choose to just say, hey, the thing that went in was a 1. And the thing that came out, that was a 1. Okay? Or you might choose to just put some parentheses with a comma and say, what went in was a 1 and what came out was a 1. Or you might choose to, what can we do? We could do x equals 1 and y equals 1. Right? If we were to call the things that go in x and the things that come out y, which we often do. Or we could draw a graph, and we could say when x was 1, y was 1. And we put a little point right there. It keeps track of it. It's pretty efficient. Okay? And then you keep noticing more things. -2 went in there, and what came out was 2. So you put a little thing there. -2, comma 2. Put a little point there. Right? You're doing a good job. You're worthy of your clipboard. Okay? And you just keep plotting these things, and eventually you get a graph like this, or you get a lot of points, and you start to say, hey, it looks like this factory will just like do this. If something goes in, that same thing will come out. If the negative thing goes in, the positive version of that thing will come out. And it looks like it will just keep doing that forever. And so you just draw a line and saying, all the points that I could ever plot would fall right on this line. In fact, this line is like made up of all those little points, all the points I could ever make. Okay, that's what a graph is. It's just a way for a guy with a clipboard to keep track of the things that go in and the things that come out of the function. Okay. Is that helpful? Clear up what a graph is, what a function is. Okay. All right, so now we're going to take this absolute value function and we're going to alter it. Okay. The way it is now, it's the most basic absolute value function you could possibly have. You take x, you take the absolute value. It's very simple. Okay, that's why we call this the parent function. Okay, it's like the origin of all the functions that are like that function. Okay, I call my parents, and my children are very much like me, but they come from me. I'm the originator, right? In a way. Some little alterations are made, like you take me and you make me a little cuter and smaller. You got my kids and a girl. You make, yeah, they're girls. Okay, so let's see what happens when we do different stuff to this function. You know, how does it mutate it? First we'll graph y equals absolute value of x just as a point of reference. Looks like this. And now we'll take y equals, and we'll put a negative. Put a negative right in front of that. So I want you to think of it this way, and then I want you to graph it. Okay. So here's what's happening. So here's a little factory, a simple factory. Stuff's going to go in here and come out here. So here's the absolute value of x factory. And in goes, a number, and out comes the absolute value of that number. Okay. So far it's just like this guy. Right? It just takes in a number and gives you out the absolute value of that number. But then after that, it goes into this factory. This is the negative factory. Okay? It takes the output of this right here, the output. Right? This part of it is exactly like that function over there, square root of x. But then when stuff comes out of the square root of x, when the square root, or the not square root, but the absolute value of x, when stuff is done, it gets made into a negative. Right? Imagine what that would do to all the outputs of the original function. And then out comes just negative absolute value of x. So do the same things we just did before. Do some inputs and outputs, and plot them, and see if you see a pattern. Maybe even if you feel confident, make a prediction about what the graph will look like when you compare it to this red one, this absolute value of x1. So if we look at this on the table of values, x, absolute value of x plus 2. Okay, do like 0, 1, negative 1, 2, negative 2, these are nice. But the 0 absolute value is 0. We take the absolute value and we add 2 to it, we get 2. Okay, you take 1, absolute value 1 is 1, absolute value 1 is 2. 3, negative 1, absolute value is 1, add 2 to that, you get 3 again. 2, you get 4, 2 again, you get 4 again, okay? So this function is acting very much like this function, only what? Adding 2. You got your outputs are 2 greater than the outputs. These outputs are 2 greater than these outputs. Everybody agreed on that? 2 greater, 2 more? Okay? So when we're looking at just numbers, like we're looking at our clipboard and this is how we're doing it, it just looks like these numbers are 2 more, right? I just add 2. On the graph, the output is not represented by a number that you wrote down, but a point on the graph, and the output is represented vertically, right? The y-axis, the output axis is vertical. So if we compare this point, let's call it 1, 1. Not writing very well. Call it 1, 1, which that point is on the absolute value of x. And we add 3 to it, or add 2 to it. We add 2, right? Adding 2 on the graph would mean you would go vertically up 2. And all the points would go up to this one and this one. All of them would, until the whole thing was just moved up 2 from the previous graph. Okay. So this guy moved it up 2, moved the graph up 2. The effect that it had on the numbers was making them 2 greater. The effect that it had on the output represented graphically was that it moved it up 2. What if we did minus 3? What would that do to the graph?
Bring it down 3.
Bring it down 3, right? Every point would move down 3. It would be less 3 less than it was. And in that way, the output of that function could go negative, right? It would go down 3, and some of them would be negative. But not because of the absolute value, right? The absolute value part was positive, and then we subtracted 3. Okay. Let's try another one. Y equals the absolute value of x. Now we'll look at y equals 3 times the absolute value of x. What is that one? We're going to take a few moments. See what kind of graphs we're getting. And how does that compare to the original? 1, negative 2, 2. Put in 0, absolute value is 0, multiply by 3, get 0. So that our graph of 3 times the absolute value of x won't, it'll still be down there, the origin. Negative 1 absolute value is 1, and we multiply by 3, we get 3, and put it in there. Absolute value is 1, multiply by 3, we get 3. Negative 2 absolute value is 2, multiply that absolute value by 3, we get 6. 2, and 6. So again, this function is very similar. It has like this stepping up pattern, this slopey kind of a pattern. But when we go to graph it, how does the graph compare to the original green absolute value of x graph?
Just 3 above.
Just 3 above for every point?
For every point, it's 3 times.
3 times. So 3 times and 3 above is 2 different things, right?
Yeah.
Okay, so not to be a stickler. But so this point is 1, 1, 1, 1. Okay, so when we go over to 1 for this other one, we don't go up 1, we go up 3 times as much, right? So 1, 2, 3. If we go over to 1, 2, this guy's 1, 2, we go, or not 1, 2, 2, 2. Okay, instead of going up 2, we go 3 times as much.
6.
6. 2, 4, 6. And we're about right there. Yeah. You go up 3 times as much when you look at the output. So how would you describe the change? Like, it's steeper. It's 3 times steeper. 3 times steeper than that original function. Okay. So far we've had y equals, we've put a negative to it. We multiplied it by a number, right, other than 1. Of course, there's the absolute value part. And we've added stuff to it. What did it do when we put a negative in front of it?
Just did the opposite.
The opposite. So what did that do to the graph?
Just went down instead of going up.
Yeah, it reflected it, right? It reflected it down instead of being up. It was like reflection. So it's a vertical reflection, or a flip. We can call it a flip because it's a shorter word. Okay. How about when we multiplied it by a? What did that do? We just did it. We just multiplied by 3, right? What did that do to the graph?
Go up times 3.
So it made the graph steeper.
Yeah.
And the less steeper for subtraction.
What's that?
And the less steeper for subtraction.
Oh, that's a good point. Right? If it's a bigger number than 1, then obviously our outputs are going to be greater than the original outputs. But if it's a number like 1/2, then these outputs, instead of being 3 times as big, they'll be half as big, right? So they would be half the way to the outputs of the original, and so we'd have a half as steep graph. So that's a good point. Steeper if a is bigger than 1, and less steep if a, let's say it's less than 1, but it's, let's say, bigger than 0. Kind of goes without saying. What about adding a number k? What did that do to the graph?
Change the placement.
The placement vertically? Yeah, so it shifted it vertically. Okay. And the last one, the last thing we could do, y equal absolute value of x, just as a reference. And y equals the absolute value of x plus 2. Notice this is the first time that we've done something to x before the absolute value gets taken. Everything else has been, we take the absolute value, then negative. Absolute value, then multiply by 3. Absolute value, then add 2, whatever. Okay? So this is a little different. So why don't you do a few points, maybe try some negative ones and some positive ones. Plug in for x, and see what comes of it. so I filled in things that we were pretty sure of by now. Absolute value of -3 is 3, and so on. Okay. But the interesting thing about this one that's different from the rest of them is that we put x in, then we do something, kind of do something to x, and then we take the absolute value. So that's definitely going to change something. We're not changing the input. The input is still -3. But we are changing what we take the absolute value of. Right? We don't just take the absolute value of whatever we put in. We take the absolute value of 2 more than what we put in. So -3 plus 2 is -1. And the absolute value of -1 is 1. -2 plus 2 is 0. Absolute value is 0. -1 plus 2 is 1. Absolute value is 1. 0 plus 2. 1 plus 2. 2 plus 2. But look at this. This is getting the same outputs, exactly the same outputs as this function, only it's like, it's off a little bit. It's shifted 2, right? It's a shift of 2. Let's look at what that looks like on the graph. And an input of -1, I guess we'll start at -3. Put an input of -3, we get 1. Input of -2, we get 0. Input of -1, we get 1. Input of 0, we get 2. 1 gives us 3. And 2 gives us 4. So it looks just like that graph, but how's it different?
Shift it over.
Shifted over, not up, not down, but over, right? Left and right shift, horizontal shift. The thing that might be surprising is that we added 2, which is a positive thing to do, not negative, and it went to the left. Like, you might think that it would move to the right. But we could look at it like this. This guy right here is a nice reference point. This point where it comes down and goes back up, we call this the vertex. All right, now the vertex is at the origin, right? Where's the vertex going to be for something like the absolute value of x plus 2? Well, that's going to be over there. In order to get a 0 to go in here, right, that's where we're going to find the origin, or the, not the origin, but the vertex. In order for this to be 0, what do we have to put in for x? Got to go over to -2 to get that to be 0. So there's your shift to the left. Okay, so we'll make some room. Move this over. And for the opposite of what you might think happens. Put -k or -h. Okay. So if we subtract, we always make sure we're subtracting, whether we subtract a positive number or subtract a negative number, which we see with adding. We can say that we move horizontally h amount. Okay. And if it moves over h, right, over to h, and it moves up k, this is where you'll find your vertex. So we put these things in combination, we'll make a horizontal shift and a vertical shift. That'll move the vertex over to the left 3 and up 5, and there it'll be at -3, 5. And then everything else will follow from there. Okay. Well, we got this little add-on, 2.7 extension. About piecewise defined functions. And not surprisingly, piecewise defined functions are defined in pieces. Here's how that goes. Use here for reference. So first, we are going to cut it into pieces, and by that we mean decide where on the x-axis are we going to say, like, for this part we'll do something, and for this part we'll do something else. For this part of the graph, we'll use one kind of function, and for this part of the graph, we'll use another kind of function. Okay? Well, how would we describe this region to the right of this division? What could you say about all this stuff over here? Greater than what? What's greater than 2? X is greater than 2. X is greater than 2 to the right of this line. And what would you say about the stuff over here? X is less than 2. So for some of it, X will be greater than 2. Well, let's go in order here from left to right. So for some of it, X is going to be less than 2. For some of it, X is going to be greater than 2. That's the first part of it. That's the first simple part about piecewise defined function. It's kind of the pieces. Some X value is like, you just cut a knife right through there. It's kind of the 2 pieces, or 3 pieces, or 4, or however many pieces you want. Okay. So the way we write this out is for this piece, if x is less than 2, we're going to use this function. Negative 1/2 x minus 1. Highlight this and maybe it's blue so we can color code this whole thing. So if x is less than 2, we'll use this function, negative 1/2 x minus 1. So how do we graph that function? What's that graph going to look like? We've been graphing them for a while now. Be a line, right? mx plus b. How do we graph that line? Negative 1 y-intercept. Then what? Down 1 to the left 2, or down 1 to the right 2? Go to the right 2. So down 1 to the right 2, we'll put a little dot right there, and that allows us to draw our line. And so that line looks like a normal line. We can cover up this part of it. It looks like, oh, that's just a line, and then when you take away, you realize the line stopped at 2, and that's what we're saying. If x is less than 2 up until 2, use this function. Okay? And then over here, we're going to use a different function. We'll do it in green, and we'll use the function 3x minus 7. 3x minus 7. What kind of graph is this going to be? A line as well?
Same thing.
Same thing?
It's on the, it's gonna be greater than x.
It's going to be greater than, x is going to be greater than 2, right? We're only going to graph it over here.
Yeah.
We still are going to use the y-intercept and the slope and all that kind of stuff to help us along, but we just won't color it in, right? So down 1, 2, 3, 4, 5, 6, 7, that's helpful. And the slope is 3, up 3 and over 1. And then up another 3 and over 1, right? And up another 3, 1, 2, 3 and over 1. And now we can draw our line, because now we're at x is greater than 2. And it's okay that they don't meet up. They don't have to meet up. That's not the way piecewise defined functions have to work. It's just that they're cut into pieces. And for one piece we use one function, and for another piece we use another function, and maybe for a third piece we use another function. Okay. The last thing to say about this is that it's not quite all the way complete. Because we have for x is less than 2 and for x is greater than 2, and that's a lot of numbers. What number have we left out? What x value has not been included yet? 3? How about 3? Yeah, 3 has an output. 1. Here's 1. That has an output.
0.
0. There it is. 0, negative 1. 2. What about when x is 2? We haven't defined that, right? So this is number 6 in the extension. It says when x is greater than or equal to 2, we'll use that function. And here's how we show that on the graph. Filled in circle, right? Remember from our number lines? And then to show that we're not going to use the other function, what do you think we use on that one?
Open
open circle right there to show, hey, we're not using that function when x is 2, we're using this function when x is equal to 2. So we put it all together with a curly bracket, and that's the function. Okay? So instead of writing this to start with, and it looking pretty confusing, we started with a picture and worked our way backwards, so hopefully that makes more sense. Okay? This defines the pieces, and these are the functions that you use. This is the definition. Right? Piecewise defined functions. So that's what it's, when it says 2.7 ext, that means there's a couple of pages right after 2.7. That's it. Have a good day. Have a good weekend.
So the XT is not extra credit. Okay.